This is a little bit more difficult now. So we're going to be creating linear equations, a system from a word problem. A little more difficult, but also very, very important. I do see this show up in the CASP. Most of you guys in math analysis, though, are seniors, so don't have to worry about the CASP, but it shows up for a reason. It's because it is an important topic. You know, one of those few things in your high school math that you could use in real life if you figured out how to use it in real life, right? So as you get better and better and more comfortable with these, you could figure out a way to use them in real life. So Michael uses a blend of dark chocolate and milk chocolate to make the ice cream topping at his restaurant. He needs to buy 100 kilograms of chocolate in total for his next order. So what does that tell me? We don't know how much dark chocolate he's going to buy. Call it D. Plus, however, milk chocolate. We just know that if you were to add the two up, it would be 100 milligrams. Or kilograms, right? So that's one of our equations. Now, if you read the rest of it, dark chocolate is $12 per kilogram. Milk chocolate is $10 per kilogram, and he wants $1,120 total. So if you think about it, however much dark chocolate we decide that he buys, it's $12 for each one, plus however much milk chocolate he buys, it's $10 for each one. Figure milk chocolate would be a little bit more expensive, but who knows? So this would represent how much total he's going to spend. $12 in the dark per amount of dark chocolate, per kilograms of dark chocolate, $10 for each kilogram of milk chocolate. So the total he spends, though, needs to be $1,120. So that's why we associate the $1,120 is the amount spent. We associate with our price function, basically. So this is like our cost function. This is like our total chocolate function. We have two different functions going on here. So just to make sure we pick the right one, because they all look like just jumbled up versions of the same thing. It looks like 8 is the exact same, and you can see they switch things up, just small little details, so be careful. But if you wanted to solve this, you would literally just enter this in Desmos, and you would get instead of D and M, you put X and Y, and the X and Y would be the solution, how much dark chocolate, how much milk chocolate you should buy. And this type of stuff, I know it sounds crazy, but you could use in real life. So look at this one. Fred is 4 times as old as Nathan and is 27 years older than Nathan. Let F be Fred's age and N be Nathan's age. So we kind of have two different functions here. We have that Fred is 4 times Nathan's age, and it's actually little f, right, for Fred. We also know Fred is 27 years older, so it'd be N plus 27, right? So that also looks like A. So you just read these, be careful. You know, here it's saying Nathan's 4 times the age of Fred, but no, Fred's 4 times the age of Nathan. Last one, Courtney walked from her house to the beach at a constant speed of 4 kilometers per hour. Sounds like more of an MX plus B problem, giving us that rate. And then walked from the beach to the park at a constant speed of 5 kilometers per hour. The entire walk took 2 hours, and the total distance Courtney walked was 8 kilometers. Let B be the number of hours it took Courtney to walk from her house to the beach, and P be the number of hours it took her to walk from the beach to the park. So B and P are the number of hours, right? B is the number of hours it took her to walk from the house to the beach. P is the number of hours it took her to walk from the beach to the park. So we know this entire walk took 2 hours. So that means if you were to take B plus P, that's the total time, because B represents the hours, P represents the hours. That total time is 2 hours. Oh, wait, my 2's are looking worse and worse. That looks better. I should just go with the classic 2, right? Now, what about distance? We know the distance was 8 kilometers. Well, we have a rate. Distance equals rate times time, right? Distance equals the rate times the time, which makes sense. You know, how many miles did you go? If you're going 60 miles per hour, your distance would be the 60 miles per hour times how long you did it. So if we want her total distance, which was 8 kilometers, well, we know that it was from her house to the beach. B is the walk from her house to the beach, right? So 4 kilometers per hour for B hours, plus we had 5 kilometers per hour, that's the walk to the park, for P hours. And the total distance is 8. So this represents the distance to the beach, this represents the distance to the park, because we have 4 kilometers per hour for this amount of time plus 5 kilometers per hour for this amount of time equals a total of 8 kilometers. So that's what we're going to be looking for. So this one takes a little bit, I haven't seen a problem like this before, so it took me a little bit more thinking, but that's pretty much it. You just have to be careful of the details. That's why I went back to double check that to the beach was 4 kilometers, to the park was 5 kilometers, just to make sure it does stick with that. And that's pretty much these problems. Just be careful and model each one. Just like we did before with modern linear equations, we just got more than one going on.